So thank you very much. So I'd like to welcome you again to our Indian Summer University in Leipzig. Yes. Yes, first of all, before we continue, I'd like to introduce myself. My name is Arndt Stephan, see it on the table. I am a professor for electrical railway systems in the Dresden University. Electric railway systems, that includes electric vehicles and electric propulsion systems, and the entire electric power supply system. That means power production, power transmission, power distribution, catenary and return current systems, and the overall system with all the things in between the subsystems. I have the honor to lead through the next presentations. Our thematic session is Optimized Energy Use and Storage Systems. Our first speaker will be Mr. Sven Klausner from the Fraunhofer Institute for Traffic and Infrastructure Systems in Dresden. Since a couple of years, he has done research and development works regarding energy storages and energy storage devices, applications in electric vehicles. His doctor thesis will be finished end of the year, maybe, I hope so that we will have more detailed information in the next year, Mr. Klausner. I hope so. And we are glad to have you here. And please, your presentation. And after the presentation, we have time for discussing. Thank you, Mr. Klausner. It's your take.
In my presentation, energy saving potential, I will understand as a ratio of so far unused braking energy to the energy demand of the vehicle. Of course. And first of all, if you're dealing with the question to decrease the energy efficiency of your tram or trolley network, is to answer the question, is the potential of unused braking energy in my network high enough? If you answer this question with yes, you have to look with which technology you can make the not used braking energy accessible for your process. And I want to give you some reason why the supercapacitors should be the best solution for this case. And then, if you defined the energy storage system, you can use a network simulation to make a better calculation if you have the energy systems well defined. The network simulation is very expensive in time. Expensive in cost and extensive in time, so you have to think about before you do something like this. Let us take a closer look on the received results. I was trying I have tried to classify our measurements results for a better overview and to make clear the main influence factors. On the one hand, we'll find results subdivided in groups of temperature, ambient temperature, the value for summer operation. I was choosing above 15 degrees centigrade, and for winter operation below 5 degrees. And the subdividing in urban center and suburban center area is a bit subjective because there is no real border between suburban area and urban center. But what I want to say is if you will meet a distributor of or a factor of it's not working again. Sorry. Distributor of energy saving.
Film.
That's not all right?
Yes.
Okay.
To film, you have to stay on the microphone.
Yes. It's horrible not to move. If you would meet with a manufacturer of energy saving systems, he will show you this amount in the right corner. And if you are an infrastructure specialist who might be thinking about energy saving systems, he would take a look on the left, on the circle in the winter urban center. But the only one result which the tradesman of a transport company will be dealing with, that's the averaging about all of the network, and all of the year it's in the middle of the diagram. Yet. Based on our experience, it can be said that the energy saving potential is significantly influenced by the network topology on the one side and by the ambient temperature on the other hand. And here you can see the complete modeled electrical network, and you can recognize all but nothing, as I guess, expect the substations only, 3 substations. That's why I will show you just the part of the network it is supplied by the substation west. And now you can find all you need, the substation, input leads, input cables, of course, breaker, couplings, and all of the components have defined nodes in the network, and they have a specified local position as well. All cable lengths are represented by transfer resistances. Can I? Like this, yes? And you can imagine how much effort you have to do to create such a network, even in this case of ebus, which a very little network. That's why you have to think about very good, will I have such a simulation or not? To repeat, summary to repeat, if you want an answer of the question if the energy potential by so far unused breaking energy is not worthy in your electrical network, I would prefer to measurement and data processing. The other 2 requests I want to bring closer to you are shown in front of you, which means for economic utilization of available breaking energy for decreasing the energy demand, a custom designed dimensioning of energy storage component and power electronics is required. An appropriate base for the decision process for the track and fleet specific purchase of energy storage system can be worked out by network simulations. That can be done by for stationary or mobile energy storage system as well. Okay, thank you very much for your attention. And question and comment.
So let's see first of all what supercapacitors are. As it has already been said, they are an energy storage system that in electric vehicles is put directly on board. So here is the structure of supercaps. You probably know how a normal capacitor is made. There are usually 2 plates at the 2 opposite in which the electric charge is stored. And the amount of electric charge, so the capacitance of the capacitor, it depends actually on the surface of these plates, because on that surface the energy is stored. It's quite different with electrochemical double-layer capacitors because the energy is not stored on a plane surface, but on this porous material that is usually activated carbon or a synthetic material. And the overall surface that is available for the storage of the electric charge is the surface of the pores. This means that in a relatively small amount of volume, we have a high storage capacity that is hundreds of times the one of a conventional capacitors. What are the operational advantages of supercapacitors on trolley buses? As it has been said, they are a system that recovers kinetic energy during the braking phase of the trolley bus. And this is a really efficient process, as storing the energy in the supercap system and releasing that allows more than 90% of the energy produced by the engine to be given back to the engine itself. So it's a really efficient process that can also be improved. As a result, the overall operational energy saving expected is more than 25%. And it's quite a lot if we consider especially the number of passengers carried by every trolley bus. For example, in Parma, on line 5, we carry usually 13,000 of passengers per day. And this energy saving corresponds to more than 3,000 of passengers. So it's actually a significant result. And this is the reason, a good reason to invest further in this technology. The figures are very good also for diesel operation. For example, for service trips between terminal and depots, we will use an auxiliary diesel engine. And in this case, the saving will be of 22%, the same, so really high. We have also energy saving on the brakes resistors that improve the reliability of the brake system, and some other relevant operational advantages. First of all, the reduction of overloads in substations, as the energy needed for acceleration in the first phase is mostly given by the supercap storage system. We have also reduced risks of electric arcs that are a very undesirable phenomenon. Trolleybus drivers are usually well trained to avoid that, but supercap technology gives us some more safety about this important phenomenon. And optionally, we can also achieve an improved reliability of onboard devices, such as air conditioning. The reason is that part of the energy stored by the supercaps can be provided directly to the control unit of the onboard devices, so that we have no interaction in feeding these delicate components while passing under neutral sections. So if we consider the overall operational cost of supercaps, perhaps a significant save can be done also in maintenance, both of the overhead lines because of the reduction of electric arcs and of the onboard devices. So it will be interesting to see over the years how much can the supercap cities save on these maintenance costs. First of all, we have to define a basic circuit model. This one is really easy. We see the voltage source, some resistors, and this C represent actually our supercap system with its internal resistor. The CP and RP represent the secondary effects of the operation of the supercap. This basic model is useless to make significant computing, so tests have to be done on supercaps to identify their behavior, for example, in different conditions of voltage and temperature. And once these tests have been done for a specific model of supercap modules, the circuit is improved in order to be solved to get reliable test results. This is only to show you an example of how complex can be a refined model for the computing of the supercap's behavior. Usually specific software are required for the solution of this model, but what we achieve with these models is quite a reliable forecast of the behavior of supercaps in operation. And then comes the most interesting thing. We finally install our supercaps on the trolley buses and put them in operation. Also for on-road tests, as the one conducted both for Milan and Parma trolley buses before official service. On every trolley bus is installed a diagnostic help unit that gives a very detailed report on the behavior of the supercap system. This is not only done in tests, but also in everyday operation. For example, the Van Hool trolley buses of Parma will enable us to know the most important data at 5 intermediate points between each stop. So TAP will be enabled to collect quite a good amount of data and perhaps work on how to improve the driving conduct of the drivers in order, or the layout of the intersection in some points of the city to make the supercap technology even more effective. We will see whether this will be possible in the future. The result of these diagnostic recordings are such graphs, and as the last thing I would like just to show you one of these. Please consider this black curve. This is the speed. This is our point of view to understand the behavior of the supercaps. Here we are in the speeding up phase, and we see that there is a steep increase in the blue curve as the current taken from the overhead line, but also a decrease of the supercap voltage, that is the purple line, because the supercap is providing its energy to the traction unit. As long as the trolleybus starts slowing down, the supercap voltage increases again as it is actually charged. And another interesting thing to see is the red curve, because that represents the overhead voltage. There is a steady and sudden drop in this part. This is probably because the trolleybus is passing under a neutral section. But we can see that nothing is modified in the behavior of supercaps, as there are no deviations in the purple curve. This means that supercap operation is not influenced by the presence of neutral sections. On the contrary, they can cooperate to avoid the negative effects of neutral sections, as they are able to store energy the same in the tracks, and on the reverse side to provide energy to continue the operation of the units when they're moving. And this might be really useful, not that much in Parma, as we have not too long neutral sections, but in other cities. An Italian example, for example, is Bologna, where for drivers is quite difficult to go through these long neutral sections placed at busy intersections. And the supercaps will reduce as well the risk of getting stuck with the trolleybus in the middle of the intersection in peak hours. So this was my overview. I thank you for this session. This is my contact. And if there are any questions, I can probably answer together with the others. So thank you very much for the attention.
So well, let's start with the first part, that is the engineering demand as stochastic process. What we already know and what we already do are conventional approaches for the energy demand. So the energy demand we can in conventional ways with a deterministic value, mostly in these 3 ways: theoretical approach, empirical approach, or measuring. Theoretical approach, this means calculation with formulas from vehicle dynamics of the train resistance, and then energy for auxiliaries and energy for heating. I think about this special issue we will hear something in the next presentation by Sascha Giebel, so the agenda is told that he will focus on that. Well, the next one is the empirical approach. Empirical approach, this means having a look to the literature, what is written there, what is given there for figures. And you normally get average information, generalized data, like written here, is although a conventional approach. And the third approach, you might have seen this figure, now it's in German, but you have seen it in English by the presentation, or by the last presentation by Mr. Klausner. There you can make measurements, Fraunhofer IVI did that, or do that, and get these results. I won't focus on that, you have already heard. Well, all these approaches have one disadvantage. One important disadvantage is because they don't consider the many influencing factors, the many influences in total. So these are the influencing factors for infrastructure and vehicle parameters, like the topology of the network, like the auxiliary power demand, these are environmental conditions, sorry, like extra energy demand for heating, etc. These are also timetable and driving style of the driver. We also have heard it in the presentation before, as well as the influences on operation cycle by traffic lights and other traffic. And this is very important because every additional stop needs a very huge amount of additional energy. I showed you in my presentation this integrated approach for dimensioning the power supply of these local public transport with electric vehicles in catenary-free operation with this onboard storage system and with these recharging points. And the whole engineering chain has these three main parts that we have to look to the energy demand as stochastic model or as stochastic value. Then I have showed you the dimensioning of the vehicle energy storage system. And then at the end I have shown you the method of dimensioning the wayside power supply. For all these methods, the energy distribution functions are required, of course. And I think with the help of these methods, the development path to electromobile in catenary-free operation, as I said in the beginning, can be or will be strengthened. And so I believe that not only buses, but also trams, not only trolley buses, but also grand-sized trolley buses can be operated by such a system, by such a CFO system with onboard storage system and recharging points, when the development of the energy storage technology will go on like in the last years. So and then it will be feasible to operate different bigger sizes like trams, big trolley buses, and vehicles like that. With these words, I finish my presentation and may say thank you for the attention.
Good afternoon, ladies and gentlemen. I'm delighted to be here today to talk to you about the influence of the onboard electrical system for efficiency improvement of electrical vehicles. What are the functions of an onboard electrical system? So here you can see a train. Here are marked, it's a regional train, and here are marked a lot of loads in the onboard electrical system. Known functions are, or some of the known functions are the generation of non-electrical power, the entrance, entertainment, air conditioning, lighting, communication, cooling, system controlling, for example. So there are many functions and many consumers. If we look on the focus to the electric railway systems, we know that the onboard installed power lies between 8 and 12% to the total power of a train. You can see here in some standards there are defined some power ratings. For example, I think you can't see it. For coaches, we've got 50 to 80 kVA. For motor cars, 300 to 400 kVA. And for power heads, 700 kVA. Yes. There are a lot of improvement strategies for HVAC systems. I want to show you some. The target is always, or in the most cases, that we want to reduce the energy consumption by maintaining the comfort. There are strategies, for example, use fresh air for cooling, heat pumps, heat recovery, demand control, fresh air supply. Can optimize the thermal insulation, can enlarge the set point adjustment, as I told you. The load control for compressor, adjust door opening time, and so on. One example I want to show you for the energy savings, reference to a passenger coach I found in the literature. So you can see the fresh air cooling, it's opening the window, makes 3 to 8%, and as you can see here, the heat pumps is the most efficiency possibility. Okay, heat recovery and demand control, fresh air supply are also between 20 and 40%. I have to say that this is only one case and under many conditions. So you can't say the results are always the same. The results often depend on the vehicle, the topology, the track, the climate, the operation focus, and so on. So this is only one example for this coach. The efficiency improvement of the onboard electrical system is you've got a lot of different options in the system level, in the functional groups, and in the unit level, and you've got an interaction between all these different groups. You have to check the necessary of standard set points, for example, in operation, and the results of your efficiency improvement depend on many different conditions, as I told you. So the further interesting fields are that we've got a variety of goods. So we have a lot of types of network configuration in voltage, function, and size, and we have a lot of different electrical vehicles with similar electric structures. So I mean, the trolleybuses, the trams, the trains, and the e-cars have sometimes similar structures. We have to see the bigger picture and have to compare them, because, for example, e-cars with their own storage system already had load management with very less power, and the big trains with much power, over 2 megawatts, don't have a load management. So we have to think about future strategies for the development of efficiency strategies are the analyzing of the consumers. We have to know, or we have to measure power, function, and the runtime of our electrical consumers. And we have to investigate the interaction between these consumers. So the system approach, I think, is the best case. So I will thank you for your attention, and I hopefully can answer your questions.